Close your eyes or soften your gaze and imagine a quiet night. The air is still. The world feels distant. Above you, the sky stretches wide and dark. Small points of light begin to appear, one by one, slowly filling the darkness. These lights are stars. Some are close, in cosmic terms. Others are unimaginably far away. Even though they look similar to your eyes, they are not all the same. Some shine brighter. Some flicker gently. Some seem almost still. This quiet sky has been observed by humans for thousands of years, across different cultures, across different times. People have looked up and wondered, what are these lights? How far do they go? And what lies beyond them? For most of human history, there were no clear answers. Only careful observation and quiet curiosity. The night sky appears calm, but it is not empty. It is filled with structure, with motion, with history. Even though it feels still to us, everything in the sky is moving. The earth rotates slowly beneath you, causing the stars to drift across the sky. This movement is steady, predictable, gentle. If you watch long enough, you would notice the stars changing position. Not quickly, but gradually. This slow movement has guided travelers, marked the passage of time, and shaped calendars. The sky feels like a dome, curving overhead, holding the stars in place. But this is only how it appears. In reality, there is no dome, no surface, just open space. The stars are not attached to anything. They exist independently, suspended in vast distances. When you look at a star, you are seeing light that has traveled for years. Sometimes hundreds of years, sometimes thousands. The light arrives quietly, without sound, without urgency. It simply reaches your eyes. This means that when you look at the night sky, you are also looking into the past. Not the present moment, but a delayed image of distant objects. The farther away something is, the older the light you see. This idea can feel unusual at first, but it is a simple consequence of how light travels. Light has a finite speed. It does not arrive instantly. So distance becomes a kind of time. The night sky is not just space. It is also history. As you continue to imagine this quiet scene, notice how peaceful it feels. There is no noise from the stars, no visible motion at first glance, just a steady presence. This stillness is part of what draws people in. It allows the mind to slow down, to rest, and to observe without pressure. The scale of the sky is difficult to grasp because it has no clear boundaries. You cannot see where it ends or where it begins. It simply surrounds you, extending in all directions, far beyond what the eye can detect. Even the darkest areas of the sky, where no stars are visible, are not truly empty. They contain faint objects, distant galaxies, and subtle forms of matter. But these are too dim to see without instruments. So, to the human eye, they appear as quiet darkness. This contrast between light and dark creates a sense of depth, a feeling that the sky is layered and vast. If you stay with this image, the stars may begin to feel less like distant objects and more like part of a larger whole. Not separate points, but elements of a continuous universe. This universe does not center around us. It does not revolve around Earth. Earth is simply one small part within it, a planet orbiting a star, which is itself one of many. This realization can feel humbling, but also calming. There is no need to rush, no need to fully understand everything at once. Just noticing the scale is enough. The night sky invites slow thinking and gentle curiosity. It does not demand answers. It simply offers questions. Questions that have been asked many times before and will continue to be asked. Over time, humans have developed tools to study the sky. Telescopes allow us to see more detail, to observe objects that are too faint for the naked eye. These tools extend our vision, but they do not change the fundamental quiet of the cosmos. Even the most powerful telescope still looks into a silent expanse. The deeper we look, the more we realize how much there is to learn and how much remains unknown. This is not a problem. It is simply part of the process. The universe does not reveal everything at once. It unfolds slowly, through observation and careful thought. As you continue to imagine the night sky, let the sense of scale settle in. Not as something overwhelming, but as something steady, something constant. The stars will remain, long after any single moment has passed. Their light will continue traveling, crossing vast distances, reaching observers in different times. This continuity connects us to the past and to the future. In a quiet and indirect way, without effort, without urgency, just through the steady movement of light. If you were to remain under this sky for a long time, you might begin to notice patterns. Groups of stars forming shapes, known as constellations. These patterns are not physical groupings, but visual arrangements from our perspective. The stars in a constellation may be very far apart, at different distances, yet they appear connected. This reminds us that what we see is shaped by where we stand. Our viewpoint matters, even in something as vast as the cosmos. As the night continues, the sky slowly shifts. New stars rise, others set below the horizon. This change is gradual, almost unnoticeable moment to moment. But over time, it becomes clear. The sky is not fixed. It is part of a dynamic system. Yet the motion remains calm. predictable. There are no sudden changes, no abrupt shifts, just a continuous flow. This steady movement reflects the nature of the cosmos itself. Large-scale processes often occur slowly, over long periods of time, far beyond human lifespans. This is why the universe can feel both active and still, because its changes are not immediate, but gradual. As you rest with this idea, notice how it affects your sense of time. The pace becomes slower, more relaxed. There is space to think, and space to simply observe. The night sky does not require interpretation. It allows quiet attention. This gentle observation is where many discoveries begin, not with urgency, but with patience. With time, humans began to ask deeper questions. Not just what is in the sky, but what the sky itself represents. Is it finite or infinite? Does it have a structure, or is it uniform? These questions lead naturally into a broader idea, the idea of the cosmos as a whole. The word cosmos is used to describe everything that exists, not just the stars above you, but all matter, all energy, all space, and all time. It includes what we can see and what we cannot see. It includes what we understand and what remains uncertain. When we speak about the cosmos, we are speaking about the totality of existence. Everything that has ever existed, and everything that ever will. This idea can feel large, but we can approach it slowly, one layer at a time. We begin close to home, with the Earth. The Earth is a planet, a sphere of rock and water, orbiting a star. That star is the sun. The sun provides light and energy, supporting life on Earth. Around the sun, there are other planets, some smaller, some larger. Together, these planets form the solar system. The solar system is a local structure, a small neighborhood in space. Beyond the solar system, there are many more stars. Each of these stars may also have planets. These stars are part of a larger structure, called a galaxy. Our galaxy is known as the Milky Way. It contains hundreds of billions of stars, spread across a vast region of space. The Milky Way has a shape, a flattened disk with spiral arms. Our solar system is located within one of these arms, far from the center. Even at the scale of the galaxy, we are not at a central position. We are simply somewhere within it. If we move further outward, we find that there are many galaxies. Not just a few, but billions. Each galaxy contains its own stars, its own systems. These galaxies are separated by large distances, yet they are part of a larger structure. This larger structure is the observable universe. The observable universe includes everything we can, in principle, detect, based on the speed of light. Because light takes time to travel, there is a limit to how far we can see. This limit is not a physical edge, but a boundary of observation. Beyond it, there may be more, possibly much more, but we cannot observe it directly. So when we speak about the cosmos, we often include both the observable universe and the possibility of what lies beyond it. This distinction is important because it reminds us that our knowledge has limits. Not everything can be seen. Not everything can be measured. Yet it still may exist. The cosmos also includes time, not just space. Events unfold over time, from the past into the future. The universe changes slowly. Stars form and eventually fade. Galaxies move and interact. Structures evolve over long periods. Time allows these processes to occur. Without time, there would be no change. So the cosmos is not just a place. It is also a process, a continuous unfolding. Another important idea is that the same physical laws apply throughout the cosmos. The laws that govern motion on Earth also govern the motion of planets and stars. Gravity behaves consistently across vast distances. Light travels at a constant speed in empty space. These regularities allow us to study distant objects and understand their behavior, even though they are far away. This consistency gives structure to the cosmos. It is not random in every sense. There are patterns and relationships. These patterns can be observed, measured, and described. Over time, humans have built models of the cosmos. These models are not perfect, but they improve gradually. With each observation, with each new piece of data, the goal is not to know everything at once, but to understand a little more, step by step. The idea of the cosmos can also be approached in terms of scale. Very small to very large. At the smallest scales, there are particles, such as electrons and quarks. These form atoms, which combine into molecules. Molecules form larger structures, such as planets and stars. These structures group into galaxies and clusters of galaxies. Each level builds upon the previous one, creating a layered structure that extends across many orders of magnitude. From the very small to the very large. All of this is part of the same cosmos. There is no separation between these scales, only differences in size and complexity. As you sit with this idea, notice how it connects everything. The ground beneath you, the air around you, the stars above you, all part of a single system. Not isolated, but connected through shared laws and shared origins. The cosmos is not something separate from us. We are within it, made from the same basic components, following the same physical rules. This does not make the cosmos smaller. It simply places us inside it, as participants, rather than observers from the outside. There is a quiet consistency in this view, a sense that everything belongs. Without needing to force meaning, just structure and continuity. As the idea of the cosmos becomes clearer, another question begins to form. If everything exists within the cosmos, then how did it begin? The question of how the universe began has been studied carefully over many years, with many observations. The current scientific model is known as the Big Bang. This model does not describe an explosion in space. It describes an expansion of space itself. In this model, the universe began in a very hot, very dense state. Not as a point in empty space, but as a condition where all of space was compressed. Then, over time, space began to expand. This expansion continues even now. At the earliest moments, the universe was extremely simple. There were no stars, no galaxies, no planets, only energy and fundamental particles. As the universe expanded, it also cooled. This cooling allowed particles to combine, forming simple atoms, mostly hydrogen and helium. These atoms filled the universe in a nearly uniform way. There were small variations, slight differences in density. These variations were important because they became the seeds of structure. Over long periods of time, gravity began to act on these differences. Regions with slightly more matter began to attract more matter. Slowly, very slowly, clouds of gas began to form. These clouds continued to gather material, becoming denser over time. Eventually, the first stars formed. These early stars were different from many stars today, often larger and shorter-lived. Inside these stars, nuclear reactions began, producing light and heavier elements. When these stars reached the end of their lifetimes, they released material back into space. This material enriched the surrounding regions, allowing new stars to form, along with planets. This process repeated over many generations, gradually building complexity. From simple beginnings to more structured systems. At large scales, galaxies began to form. Collections of stars, bound together by gravity. These galaxies continued to evolve, interacting with one another, sometimes merging, sometimes passing by, all while the universe continued to expand. This expansion is a key part of the model. It is not something that happened once and then stopped. It is ongoing. Evidence for this expansion comes from observation. Light from distant galaxies is shifted toward longer wavelengths. This is known as redshift. It indicates that galaxies are moving away from us and from each other. The farther away a galaxy is, the faster it appears to recede. This pattern suggests that space itself is stretching. Another piece of evidence is the cosmic microwave background, a faint signal detected in all directions. This signal is the afterglow of the early universe, from a time when atoms first formed. It is very uniform, but contains small variations. These variations match the patterns needed to form galaxies later on. Together, these observations support the Big Bang model, not as a final answer, but as a well-tested framework. There are still open questions. For example, what caused the initial conditions? Why the universe began in this state? And what happened at the very earliest moments? These questions are still being explored with careful research. It is also important to note that the Big Bang does not describe a center. There is no central point from which everything expands into empty space. Instead, every region of space expands relative to every other region. From any location, it appears that distant galaxies are moving away. This means the expansion is uniform on large scales, not focused in one direction. As you sit with this idea, notice how it changes the image of the universe. Not a burst into space, but a quiet unfolding of space itself. A gradual increase in distance between objects. This process has been ongoing for billions of years and continues now. The timescales involved are very large, far beyond everyday experience, which is why the universe can feel still, even while it changes. Slowly, consistently, without sudden shifts at human scales. The Big Bang model provides a starting point, a way to trace the universe backward in time, toward simpler conditions. As the expansion is reversed in theory, temperatures increase, densities increase, leading back to an early hot state. Beyond that, our current understanding becomes less certain. Physics at those conditions is still being studied. So there is a boundary, not in space, but in knowledge. A place where questions remain open. This is part of the mystery, not something to resolve quickly, but something to explore over time. As the universe expanded and cooled, it created the conditions for structure. Structure leads to galaxies and stars, which in turn lead to planets and environments like Earth. This connection links the early universe to the present moment in a continuous chain, from simple beginnings to increasing complexity without interruption. As you rest with this idea, the expansion continues quietly. Galaxies drift apart, distances grow, and the universe becomes larger. This ongoing expansion leads to another gentle question. How does the universe continue to change over time? The universe continues to expand, not quickly in a way we can feel, but steadily over time. This expansion affects the largest scales, the distances between galaxies. It does not pull apart smaller structures, such as planets or solar systems. Gravity holds those together. So the expansion is gentle and selective. It becomes noticeable only across vast distances. When we observe distant galaxies, we see that they are moving away. Not because they are traveling through space in the usual sense, but because the space between us is increasing. This idea can be imagined slowly, like points on a surface that is stretching. As the surface grows, the points move farther apart. No single point is the center. The expansion happens everywhere. This is a key feature. The universe does not expand into something else. It is the space itself that changes. Over time, the rate of this expansion has also changed. In the early universe, gravity slowed the expansion slightly. Matter pulled on matter, creating a gentle resistance. But as the universe grew larger, another effect became more important. The expansion began to accelerate. This means that galaxies are not only moving away, but doing so at an increasing rate. This acceleration is supported by observation, especially measurements of distant supernovae. The cause of this acceleration is not fully understood. It is often described using the idea of dark energy, a form of energy associated with space itself. It acts in a way that increases expansion, rather than slowing it down. Even though its nature is unclear, its effects can be measured. This reminds us again that not everything in the cosmos is directly visible. Some aspects are known through their influence. As the universe expands, the average density of matter decreases. Galaxies become more separated, and interactions between them become less frequent. In the distant future, this separation will continue, leading to a quieter, large-scale structure. Within galaxies, processes will still occur. Stars will continue to form from clouds of gas, though over time, the available gas will be used. Star formation will gradually slow. This is a long process, taking billions of years. As stars age, they change. Some expand into larger forms. Others collapse into dense remnants. These changes are part of a natural cycle. Matter is reused, reshaped. But overall, the universe trends toward less activity. Not suddenly, but gradually. Energy spreads out. Differences become smaller. This idea is related to the concept of increasing entropy, a measure of how energy is distributed. Over very long timescales, the universe may approach a state where usable energy is limited. This is sometimes called a heat death scenario. Not a dramatic event, but a gradual fading of processes. Stars burn out. New stars form less often. Light becomes rarer, and the universe grows darker. However, this is only one possible long-term outcome. Based on current understanding and current observations, there are still uncertainties. about the exact behavior of dark energy and how it may evolve. So the future is described in models, rather than fixed predictions. As you reflect on this expansion, notice how it connects past, present, and future. The same process that began early in the universe continues now and will continue forward. It is a single continuous motion, without interruption. Even though the scale is large, the behavior is consistent, measured, described. Through careful observation, this steady expansion also shapes how we see the universe. Light traveling across expanding space becomes stretched. Its wavelength increases, shifting toward the red end of the spectrum. This redshift is not just a detail. It is a key signal, a way of understanding motion across distance. The farther the light travels, the more it is affected. So observation becomes a form of measurement, a way to trace expansion. Without needing to move through space ourselves. As you sit with this idea, the universe feels both active and calm, expanding, yet steady, changing, yet predictable at large scales. There is no sudden motion, no abrupt shift, just a gradual increase in distance. This quiet expansion creates the framework within which galaxies exist. And within those galaxies, stars continue their slow processes. These stars are the next layer to consider. Small in appearance, yet central to the structure of the cosmos. Stars are the small points of light you see in the night sky, but each one is a large sphere of hot gas, mostly hydrogen and helium. They produce light and heat through a process called nuclear fusion. In their cores, hydrogen atoms combine to form helium. This process releases energy, which travels outward, eventually reaching space as light. This light can travel for years, or much longer, before reaching an observer. Stars form from clouds of gas and dust, known as nebulae. These clouds exist within galaxies, spread across large regions. Over time, gravity pulls parts of these clouds together. The material becomes denser and begins to collapse inward. As it collapses, it heats up, slowly forming a dense core. When the temperature and pressure become high enough, fusion begins. At that moment, a star is born. This process is gradual, taking millions of years. Once formed, a star enters a long, stable phase. During this time, the inward pull of gravity and the outward pressure from fusion are balanced. This balance keeps the star stable for long periods, often billions of years. The exact lifetime depends on the star's mass. Larger stars burn their fuel more quickly and have shorter lives. Smaller stars burn more slowly and can last much longer. Our Sun is a medium-sized star in a stable phase of its life. It has been shining for about 4.6 billion years and is expected to continue for several billion more. Over time, a star's core changes. As hydrogen is used, the balance begins to shift. The core contracts, and temperatures rise. This leads to new stages of fusion in more massive stars. Heavier elements can form, such as carbon, oxygen, and beyond. These elements are created inside stars. Over time, when a star reaches the end of its life, its outer layers may be released into space. In some cases, this release is gentle. In others, it is more energetic, but always part of natural processes. The remaining core becomes a compact object, such as a white dwarf, a neutron star, or, in some cases, a black hole. The material released by stars does not disappear. It becomes part of the surrounding space, enriching it with heavier elements. These elements can later form new stars and new planetary systems. This creates a cycle: formation, evolution, and return of material. Over many generations, this cycle increases complexity. The atoms that make up planets and living systems were formed in earlier stars. This means that star processes are directly connected to the structure of the cosmos as a whole. Even though stars appear small in the sky, they are fundamental to how the universe evolves. They provide energy and create elements, supporting the formation of new systems. Stars are not all identical. They vary in size, temperature, and brightness. These differences affect their color. Some stars appear red, others white, others blue. This color reflects surface temperature. Cooler stars tend to appear redder. Hotter stars appear bluer. These variations can be observed, even from Earth, adding detail to the night sky. As you imagine these stars, notice their quiet persistence, each one following physical laws over long periods, without interruption. The processes inside them are continuous, steady, balanced for most of their lifetimes. Even when changes occur, they unfold gradually, over spans far longer than a human life. This is why the stars appear constant, even though they are evolving. Their changes are simply too slow to notice directly. When you look at a star, you are seeing a moment in its long history, a brief snapshot of an ongoing process. This applies to all stars, across the galaxy, and beyond. As these stars group together, they form larger structures, systems bound by gravity, moving through space. These structures are known as galaxies. Galaxies are vast collections of stars, along with gas, dust, and dark matter. They are bound together by gravity. forming stable structures over long periods of time. Each galaxy contains many stars, often hundreds of billions. And each of those stars may have its own system. When viewed from a distance, a galaxy can appear as a soft glow, a faint shape in the darkness. But up close, it is a complex system with motion, structure, and history. Our own galaxy is the Milky Way. It is a spiral galaxy with a central bulge and extended arms. These arms curve outward, containing stars and regions where new stars are forming. The solar system is located within one of these arms, at a distance from the center, not in a special position, but simply part of the larger structure. At the center of many galaxies, including the Milky Way, there is a dense region, often containing a supermassive black hole. This central region influences the motion of stars through gravity. Stars within a galaxy do not remain still. They orbit the center, moving in paths shaped by gravitational forces. This motion is steady and takes a long time to complete. For example, the Sun takes about 230 million years to orbit the center of the Milky Way once. This is sometimes called a galactic year. Galaxies come in different shapes. Some are spiral, like the Milky Way. Others are elliptical, with a more rounded form. And some are irregular, without a defined structure. These shapes reflect their history, including interactions with other galaxies. Over time, galaxies can influence each other. Through gravity, they may pass close by, distorting each other's shape. In some cases, they merge, forming a larger galaxy. This process is slow, taking millions to billions of years. During these interactions, stars are usually not in direct collision because the distances between them are large. Instead, the overall structure changes. Gas clouds may compress, leading to new waves of star formation. These processes contribute to the evolution of galaxies. They are not fixed, but dynamic systems, changing slowly over time. Beyond individual galaxies, there are larger groupings. Galaxies often exist in clusters, bound together by gravity. These clusters can contain hundreds, or even thousands of galaxies. Clusters themselves can be part of even larger structures, forming a cosmic web, a network of matter, spread across the universe, with filaments and vast empty regions called voids. This large-scale structure reflects the early variations in the distribution of matter. Over time, gravity amplified these variations, leading to the patterns we observe today. Even though galaxies are immense, they are separated by even greater distances. The space between them is mostly empty, yet not completely empty. It contains low-density gas and radiation. As you imagine these galaxies, Notice their quiet motion, each one moving, rotating, interacting over long timescales, without sudden change, without urgency, just steady evolution. The light from distant galaxies travels for millions or billions of years before reaching us. So when we observe them, we see them as they were in the past. This allows us to study the history of the universe by looking deeper into space. Each distant galaxy becomes a record of an earlier time. This connection between distance and time is a key part of cosmology. It allows us to build a picture of how structures formed and changed. As you rest with this idea, the cosmos appears layered. Stars within galaxies, galaxies within clusters, clusters within a larger network, each level connected through gravity and time. Yet even with all this structure, there are still elements we cannot see directly. Forces and forms of matter that shape galaxies in subtle ways. These unseen components lead to another question. What holds galaxies together so consistently? When we observe galaxies, we notice something unusual. The visible matter is not enough to explain how they move. Stars orbit the centers of galaxies at speeds that should not be possible, based only on the mass we can see. If only visible matter were present, the outer stars would move more slowly or drift away over time. But this does not happen. The stars remain bound. Their motion is stable. This suggests that there is additional mass, not directly visible. This unseen mass is called dark matter. The term dark here means that it does not emit light and does not absorb light in a detectable way. It does not interact with electromagnetic radiation, so it cannot be seen with telescopes. But its presence can be inferred through its gravitational effects. Gravity depends on mass, whether that mass is visible or not. So by studying motion, we can estimate how much mass must be present. These measurements consistently show that there is more mass than we can observe directly. Dark matter is not concentrated only in the center. It forms a large halo surrounding galaxies, extending far beyond the visible structure. This halo provides the extra gravitational pull needed to keep galaxies stable. Without it, the structure of galaxies would be very different. The idea of dark matter is supported by multiple observations. Not only the rotation of galaxies, but also the motion of galaxies within clusters, and the way light bends as it passes through space. This bending is known as gravitational lensing. Massive objects can curve space-time, changing the path of light. When we observe lensing effects, the amount of bending often indicates more mass than what is visible, again suggesting the presence of dark matter. Another line of evidence comes from the large-scale structure of the universe. The distribution of galaxies in clusters matches models that include dark matter. Without it, the observed patterns would be difficult to explain. Dark matter appears to interact primarily through gravity. It does not form stars or planets. It does not cluster in the same way as normal matter. Instead, it provides a kind of framework within which visible matter gathers. Galaxies form within these dark matter halos, following their gravitational influence. Even though we cannot see dark matter directly, its effects are consistent across different scales, from individual galaxies to clusters to the structure of the universe as a whole. This consistency strengthens the idea that it is a real component of the cosmos. However, its exact nature is still unknown. Scientists have proposed different possibilities, often involving new types of particles. These particles would have mass, but interact very weakly with light. Experiments are ongoing to detect such particles, both in laboratories and through observations in space. So far, no direct detection has been confirmed. This means that dark matter remains a working model, supported by evidence, but not yet fully explained. As you reflect on this idea, notice how it adds depth to the cosmos. What we see is only part of what exists. There are components that do not reveal themselves through light, but still shape the universe. Quietly, consistently, without drawing attention. This unseen presence influences motion, structure, and stability. It is part of the reason galaxies hold together, and why the large-scale universe has its observed form. As you sit with this thought, the cosmos becomes more layered. Not only what is visible, but also what is hidden, both contributing to the whole. This leads gently to another idea, not just unseen matter, but a form of energy affecting the expansion itself. Beyond the idea of unseen matter, there is another observation, one that relates to the expansion of the universe. Earlier, we described how space itself is expanding, galaxies moving farther apart. Over time, for a long period, it was expected that this expansion might slow down, because gravity pulls matter together. A universe filled with matter should gradually reduce its rate of expansion. But careful observations revealed something different. The expansion is not slowing, it is accelerating. This means that galaxies are moving away from each other at an increasing rate, not due to their own motion alone, but due to the behavior of space itself. This acceleration was measured by observing distant supernovae. These events act as standard candles, allowing distance to be estimated. When these distances were compared to how fast galaxies are receding, the results showed a clear pattern. Expansion is speeding up. To describe this effect, scientists introduced the concept of dark energy. The term dark here again means not directly observable. Dark energy does not emit light and does not interact with matter in familiar ways. Its presence is inferred through its effect on expansion. At large scales, dark energy appears to act as a kind of pressure, not pulling things together, but gently pushing space apart. This effect is very weak at small scales, so it does not affect galaxies directly or solar systems. But across vast distances, it becomes significant, influencing the overall behavior of the universe. One way to think about it is that empty space itself has properties. It is not completely empty, but has an energy associated with it. As space expands, more of this energy appears, maintaining a roughly constant density. This leads to continued acceleration. The exact nature of dark energy is not yet known. One possibility is that it is related to the cosmological constant, a term in the equations of general relativity. Another possibility is that it changes over time, in ways not yet fully understood. These ideas are being studied through observation and theory. Measurements of the cosmic microwave background and large-scale structure also support the presence of dark energy. Together, these observations suggest that most of the energy content of the universe is in this form, while ordinary matter makes up only a small fraction. This can feel unusual because what we see directly is not the dominant component. Instead, the largest influence comes from something we cannot observe directly. Yet its effects are consistent and measurable. As you reflect on this, notice how the cosmos includes both the visible and the inferred. Both are part of scientific understanding. Based on observation, careful measurement, and repeated testing, dark energy does not act suddenly. It does not create abrupt changes. Its influence is gradual, spread across the entire universe, affecting the largest scales over long periods of time. This contributes to a quiet transformation, the increasing separation between galaxies, a slow stretching of the cosmic structure. As the universe expands and accelerates, distant galaxies will eventually move beyond observable limits. Their light will no longer reach us, not because they disappear, but because the space between grows too quickly. This does not happen suddenly, but gradually, over extremely long timescales. As you sit with this idea, the universe feels both expansive and subtle, changing continuously, yet without urgency. The presence of dark energy adds another layer to the structure of the cosmos. Not only matter shaping space, but space itself influencing motion. This balance between components creates the universe we observe and continues to guide its evolution. As this understanding deepens, another concept comes into focus: regions where gravity becomes extremely strong and space behaves in unusual ways. In some regions of the universe, gravity becomes extremely strong enough to change how space and time behave. These regions are known as black holes. A black hole forms when a large amount of mass is compressed into a very small space. Often this happens at the end of a massive star's life, when the star can no longer support itself against its own gravity. The core collapses inward, becoming denser and denser. If the mass is sufficient, the collapse continues until a black hole forms. At the boundary of a black hole, there is a region called the event horizon. This is not a physical surface, but a limit, a point beyond which light cannot escape. Because light cannot escape, the black hole cannot be seen directly. It does not emit light from within this boundary, but its presence can still be detected through its effects on nearby matter. Matter that moves close to a black hole experiences strong gravitational forces. It may form a rotating disk around the black hole. This disk is called an accretion disk. As matter in the disk moves, it heats up, emitting radiation, which can be observed. This allows astronomers to identify black holes indirectly by observing the behavior of surrounding material. Black holes vary in size. Some are formed from individual stars. These are called stellar mass black holes. Others are much larger, found at the centers of galaxies. These are called supermassive black holes. Their masses can be millions or billions of times that of the Sun. In galaxies, these central black holes influence the motion of nearby stars, helping shape the inner regions. The presence of a supermassive black hole is common in large galaxies, including the Milky Way. At the center of the Milky Way, there is a black hole known as Sagittarius A star. Its gravitational influence extends across the surrounding region. Even though black holes are often described as absorbing matter, they do not actively pull objects in from a distance. Their gravity behaves like that of any mass. At a distance, objects must come close for the effects to become extreme. This means that black holes are not hazards. At large distances, they are simply part of the cosmic structure. The study of black holes has provided insight into gravity and the nature of space-time. According to general relativity, mass curves space-time. A black hole represents an extreme case, where this curvature becomes very strong. Time itself behaves differently near a black hole. Clocks closer to the event horizon appear to run more slowly compared to those farther away. This effect has been measured in less extreme situations and matches predictions. Black holes also raise open questions about how gravity interacts with quantum mechanics, two areas of physics that are not yet fully unified. For example, there are questions about what happens to information that enters a black hole. These questions are part of ongoing research. Observations have improved over time, allowing more direct study. Images of black hole shadows have been captured, showing the outline of the event horizon. These images match theoretical predictions, providing further support. As you reflect on black holes, notice how they represent limits, boundaries in our understanding, regions where familiar concepts begin to change. Yet they are not separate from the rest of the universe. They form naturally from known processes and exist within galaxies, alongside stars and other structures. Their presence adds depth to the picture of the cosmos, not only vast and expanding, but also containing regions of intense gravity. As you sit with this idea, another question begins to form. In such a large universe, with so many stars and planets, could there be other places where life exists? In a universe filled with galaxies, and within them, vast numbers of stars, it is natural to consider the possibility of life elsewhere. Not as a conclusion, but as a question. A quiet and open question. Around many stars, there are planets. These are called exoplanets, planets beyond our own solar system. Observations have confirmed thousands of them, with a wide range of sizes and conditions. Some are large, like gas giants. Others are smaller, with solid surfaces. Some orbit close to their stars, others much farther away. Among these planets, there are some that exist in what is called a habitable zone. This is a region around a star where temperatures may allow liquid water to exist. Water is important because it supports chemical processes known to be useful for life on Earth. However, being in a habitable zone does not guarantee life. It only suggests that conditions could allow it. Life, as we understand it, requires more than just the right temperature. It depends on chemistry, energy sources, and stable environments. These conditions may exist elsewhere, but they are not yet confirmed. Within our own solar system, there are places of interest. For example, Mars shows evidence of past water, and icy moons such as Europa and Enceladus contain subsurface oceans. These environments are being studied as potential locations for simple life. So far, no direct evidence of life beyond Earth has been confirmed. This absence of evidence does not mean absence of life. It simply reflects the limits of current observation. The distances involved are large, making direct detection difficult. Even light from nearby stars takes years to reach us. Signals, if they exist, would be faint and require careful analysis. Scientists search for signs of life through indirect methods. For example, by studying the atmospheres of exoplanets, certain gases, in specific combinations, could suggest biological activity. These are called biosignatures. Observations are improving with more advanced telescopes, allowing more detailed study. Over time, the ability to detect such signals may increase. The question of life also connects to probability. With so many stars and so many planets, it is reasonable to consider that life could arise elsewhere. But probability alone does not provide confirmation. It only frames the question. There is also the question of complexity. Life can exist in simple forms, such as single-celled organisms, or in more complex forms, with higher levels of organization. The conditions required for complex life may be more specific and less common. This adds another layer to the question. As you reflect on this idea, notice how it remains open, not resolved, not closed. It invites careful thought, without urgency. The universe is large and varied, offering many possibilities, but also requiring patience. As observation continues, more data will be gathered, and understanding will improve. Gradually, step by step, without sudden conclusions. For now, the question remains: are we alone, or part of a wider pattern? It is enough to hold the question, without needing an immediate answer. As you sit with this, the scale of the universe becomes more personal. Not just distant structures, but potential environments, where processes similar to those on Earth might occur. This leads gently to another consideration, not just where the universe is now, but how it may continue to change over time. The universe has been expanding for a very long time, and this expansion continues. So it is natural to ask, what will happen over even longer timescales? Not in years or centuries, but in billions and trillions of years. The answer depends on how the universe behaves overall, especially the balance between matter, gravity, and dark energy. Observations suggest that expansion is accelerating, driven by dark energy. If this continues, the universe will keep expanding, becoming larger and less dense over time. Galaxies that are not gravitationally bound will move farther apart. Eventually, they will be so distant that their light can no longer reach each other. This does not happen suddenly, but gradually, over very long periods. Within galaxies, stars will continue their life cycles, forming, shining, and eventually evolving into later stages. But the supply of gas needed to form new stars is not unlimited. Over time, this gas is used or dispersed, so star formation slows down. Existing stars will age. Some will become white dwarfs, others neutron stars, or black holes. The overall brightness of the universe will decrease slowly as fewer new stars appear over extremely long timescales. Most stars will no longer be active. The universe will contain many stellar remnants, objects that no longer produce significant light. This stage is sometimes described as a gradual fading, not a sudden event, but a steady decline in activity. As time continues, even these remnants may change through slow processes such as decay or interaction. Though these processes take extremely long periods, at the largest scale, the universe may approach a state where energy is evenly distributed. This means there are fewer differences to drive change. This idea is related to increasing entropy, a measure of how energy spreads out. When energy is evenly spread, there is less capacity for work, less structure forming, less activity overall. This possible future is often called heat death. It is not a collapse, and not an explosion, but a quiet state with minimal change. A universe that continues to expand, but with very low energy differences. However, this is only one scenario. It is based on current observations and current models. There are other possibilities, though less supported by current data. For example, if dark energy were to change over time, the expansion could behave differently. In some models, expansion could accelerate further, leading to a scenario where structures are gradually pulled apart, even at smaller scales. This is sometimes called a big rip. In other models, if the influence of gravity were stronger, expansion could slow and eventually reverse, leading to a contraction, sometimes called a big crunch. Current observations do not strongly support these alternatives, but they remain part of theoretical study. As you consider these possibilities, notice that all of them unfold slowly, over timescales far beyond everyday experience. There is no urgency, no sudden transition at human scales, just gradual change, guided by consistent physical laws. The future of the universe is not fixed in detail, but it is constrained by observation. Each new measurement refines our understanding, step by step, without rushing to final answers. As you sit with this idea, the universe feels extended in time, not only vast in space, but long in duration, stretching far beyond the present moment. This perspective brings a quiet sense of continuity, a process that began, continues, and will continue, as part of the same unfolding system. With this in mind, it becomes natural to return to a simpler view. The experience of looking at the night sky and reflecting on what it means to be part of this larger whole. Return again to the quiet night sky, the same sky you imagined before. Wide, dark, and filled with distant light. The stars are still there, steady, unhurried. Their light continues to travel across great distances, reaching you without sound, without effort. As you observe this, notice how little has changed in your immediate view. The same patterns, the same quiet presence. even though, in reality, everything is in motion. The Earth turns slowly beneath you, completing one rotation over many hours. The stars shift position across the sky. In a gradual arc, the Milky Way itself rotates over hundreds of millions of years. And beyond that, the universe continues its quiet expansion. Yet none of this feels urgent. None of it demands your attention. It simply continues, with or without observation. This contrast between motion and stillness is part of what makes the night sky calming. Activity exists, but it unfolds slowly, at a pace that allows the mind to rest. As you remain with this image, let your attention move gently from one point of light to another, without needing to name them or categorize them, just observing their presence. Each point of light represents a star, or in some cases, a distant galaxy. The distinction is not always visible to the unaided eye, but both are part of the same cosmos. The same system described earlier, a system of structure, motion, and time. As these ideas settle, there is no need to hold them tightly. They can remain in the background, like the stars themselves, present, but not demanding. The concept of mystery may come to mind. The idea that there are things not fully known. This is a natural part of understanding the cosmos. Not everything has been explained, and not everything needs to be. Some aspects remain open, available for future study. This does not create instability. It simply reflects the limits of current knowledge. Science works gradually, through observation, measurement, and refinement. Ideas are tested, compared with evidence, and adjusted when needed. This process takes time, often long periods of time. So the presence of unanswered questions is expected. It is part of the structure of inquiry. As you reflect on this, the unknown becomes less sharp, less urgent. It becomes a quiet space, rather than a problem. A space where future understanding may develop, or remain open, without difficulty. The cosmos does not require completion. It does not need to be fully explained, to be observed, or appreciated. It simply exists, with structure that can be studied, and with aspects that remain uncertain. Both can exist together, without conflict. As you continue to imagine the sky, consider the idea of connection. The atoms in your body were formed in earlier stars. Through processes of fusion over long periods of time, these atoms were released into space, incorporated into new systems, eventually becoming part of planets and environments like Earth. This connection is not symbolic. It is physical, a direct link between stellar processes and present structure. The same elements, The same laws of physics apply across scales, from stars to planets to living systems. This continuity creates a stable framework, one that does not change abruptly, but evolves gradually. As you sit with this idea, the distance between observer and cosmos becomes smaller, not in space, but in understanding. You are not separate from the system. You are within it, following the same physical rules, participating in the same processes. This does not reduce the scale of the universe. It simply places you inside it, as one part among many. There is a quiet consistency in this view. Nothing stands outside the system. Everything is included. The stars above, the ground below, the air around you, all part of the same continuous structure. As time continues, the universe evolves. Galaxies move. Stars change. Expansion proceeds. These changes are real, but they occur slowly, at scales that do not disrupt the present moment. This allows for a stable experience, even within a dynamic system. The night sky reflects this balance. Motion within stillness. Change within continuity. As you observe, you do not need to track every movement. It is enough to notice the overall pattern, the steady presence of light against a dark background. This pattern has been seen by many observers across different times and will continue to be seen by others in the future. The continuity of observation connects different moments in time, not through direct interaction, but through shared experience. Looking at the same sky, under similar conditions. This does not require interpretation. It is a simple act. Observing light that has traveled across space, reaching the present moment. As you remain with this scene, let the ideas fade slightly, not disappearing, but becoming softer, less defined, like the edges of the stars themselves. The details are still there, but they do not need to be held clearly. The sense of scale remains, along with the sense of continuity. A universe that exists, expands, and evolves without interruption over long periods of time. Within this universe, observation takes place, quietly, without urgency, without the need for immediate conclusions. The mystery of the cosmos remains, not as something hidden, but as something not yet fully described. This leaves space for continued exploration or simply quiet awareness. Both are valid. Both are part of the same experience. As the night continues, the sky slowly shifts. Stars move across the horizon. New ones appear. Others fade from view. This motion is gradual, almost unnoticeable, unless you watch for a long time. This reinforces the sense of slow change, a key feature of the cosmos. Nothing rushes. Nothing demands immediate response. Processes unfold at their own pace, independent of observation. As you rest with this final image, the quiet sky above, the steady points of light, the gentle motion over time, you can allow the experience to settle without holding on to each idea, just the overall impression of a vast, continuous, and structured universe. A system that exists without needing to be fully known. And within it, a moment of quiet observation. The night remains calm, the stars remain steady, and the cosmos continues